Hi everyone, this is the Mathman TP here. I had a lot of requests for the Pythagorean Theorem, some sort of review on that. So I put together this PowerPoint and hopefully it explains everything you need. So right away, we have to know that Pythagorean Theorem only works for right triangles. And so we have to make sure that we got a right angle, and the sides of the right angle are called the legs, and the hypotenuse is the longest side, always opposite to the right angle. And if you can remember the letter L for legs, that's the 90-degree angle. We used angles when we were in the younger grades. Now we need to know more than just the fact the angles add up to 90. As I said, the hypotenuse is the side that's opposite to the right angle, and the A and the B are what we use as letters for the legs, and the C is generally used to represent the hypotenuse. Right-angled triangles were used for measurement of navigation and construction and land measurements. So here we go. Right triangles only. The order of the legs doesn't matter. So if we have those two sides labeled opposite A and B or B and A, no problem. And it doesn't matter because of the operation we're going to do is addition, and that is commutative. So here it is, the Pythagorean theorem. Reminder, did I say that already? Yeah, right triangles. A squared plus B squared equals C squared. And what that means is you take the length of the side A and square it, the length of the side B and square it, and then you get the length of the side C and square it. And you can also change the order. In words, and you might recognize this phrase, your teacher may have mentioned it, we have the square of the hypotenuse is equal to the sum of the squares of the other two sides. And that is basically the statement of the Pythagorean theorem. If you count the tomatoes in the diagram here, you can see that the square on the short side and the square on the medium side, add all those tomatoes together and you get the square on the hypotenuse. It works for circles and semicircles and triangles and everything like that. So, as I said, it was used in ancient Egypt for measurement, and it was used for pyramids and measurements of land. The main thing was they discovered it a long time ago, but only Pythagoras was the one who proved it and used it in his mathematical geometry explorations. So the first thing is, I'm giving you this triangle. Looks like it might have a right angle, but we can prove it using the Pythagorean theorem by plugging in the three side lengths, making sure that the longest side, okay, is going to be the hypotenuse. So in this particular case, it would have to be 17. You test out by squaring the other two sides and seeing whether it makes a true statement. And what do you know? It's true. The conclusion, since the Pythagorean theorem works, it must be a right triangle, and you can state that the side opposite the right angle is the longest side, 17, and label the right angle up on top. We can also use the Pythagorean theorem to find sides that are missing. The first type of example is when we're looking for the hypotenuse. So we set up the Pythagorean theorem, replace in the two legs, and we're looking for the third side, the hypotenuse. Go through the calculations. When you get to these examples, you're always going to wind up with a statement here that has a squared. And that means you're going to have to square root both sides to find out the value. Sometimes it works out evenly, not always. Next, we're trying to find the missing side here. Same deal, we're looking for the longest side, the hypotenuse, which is labeled y. Replace in the legs, square both of them, and then square root both sides. This one doesn't work out evenly, and usually you look for clues that tell you what you have to round your final answer to. What's different about this one? Well, this time you're given the hypotenuse, and so we have to look for one of the legs. The order doesn't matter. Just make sure you do a little bit of algebra here when you bring the 36 to the other side, or subtract 36 from both sides, and then square root both sides. Rounded, because it doesn't work out evenly, this time to 2 decimal places. There's another type of problem that gives students difficulty, and that's when there's two sides missing. The only time we can do this is if it's an isosceles triangle and two of the sides are equal. And we have to use a little bit of algebra here because we're going to have two sides labeled the same, and to simplify this, we have to collect the like terms. So n squared and n squared, divide first, then you're going to square root both sides, and again, I'll tell you right now, most of the time, these ones are not going to work out evenly. There are a bunch of them that do work out evenly, and they're called Pythagorean triples. And you can put them together. We saw the 3, 4, 5 with the tomatoes at the beginning. There are multiples of it that will work and create nice right triangles with 3 integer side lengths. And there are these basic ones that we have to sort of recognize or memorize because they come up so often. And it's going to be helpful to recognize them. It'll speed up your work and make it so that you're recognizing, hey, I know why this works. I recognize that triple. So there's the 3, 4, 5, the 5, 12, 13, and all of its multiples, 7, 24, 25, and all of its multiples. You might recall an example earlier on, 8, 15, 17. That one also works. There's a way of generating them. That's beyond the scope of what we need to know right now. And as you notice each time, the longest side has to be the hypotenuse, right? Opposite from the 90-degree angle. So here's a couple of applications. I'm going to go through these pretty quick. You'll have to pause to actually test them out. You get a question, read it carefully, draw a diagram. So you're told it's a rectangle, the width and length are 4 and 10, and you're looking for the length of the diagonal. You have to recognize that there's a right angle in there in the corner or up in the other corner, and you're looking for the hypotenuse. Go through the calculations and you'll see you're going to have to square root 116. Doesn't work out evenly. Does it give you some clues about what to round to? There it is, the nearest tenth of a meter. So 10.8 for the length of the diagonal. Moving on. Typical one here about driving or directions. You have to know a little bit about your cardinal points, north, south, east, west. And so he's going 20 kilometers east, 45 kilometers south, and then they're trying to find out how far he is from the original. Now, yeah, he drove 65 kilometers, but we're talking about as the crow flies directly across. Looks like I already gave you the answer here. Notice it's bigger than the 45, and you work it out and realize at the end of it all, you've got the square root of 2425. As I said, gave it away too early, 49.25, 24 kilometers. Moving along, okay? Oh yeah, don't forget, answer in a sentence with appropriate units. Here's a nice little design that is based on the Pythagorean Theorem, where the hypotenuses are all irrational numbers, except where square root of 4 comes up, or the square root of 9, or the square root of 16. Nice little snail pattern. And yes, it does mirror the way a snail or a shrimp might grow. And a couple of links that might be useful if you want to pursue it. Thanks. Hope this helped.